What we're going to look at right now with this set of notes, you can see obviously our graphing techniques, applying transformations. Those transformations will be applied to the parent functions that we have discussed in the previous set of notes. And so we're going to see a lot of the x squared, the square root of x, the absolute value of x. And we're going to look at how applying different transformations manipulates and moves those parent functions around the coordinate plane. We're going to see vertical and horizontal shifts. We're going to see vertical stretch and compressions. We're going to see reflections about the x and the y axis. And a lot of it's going to be through example. The examples that I have here are better for when we're in person in class. So I'm going to refer to Desmos a lot to kind of show you visually what we're talking about with each one of these different examples. The first one that we're going to see here is the what would be a vertical shift up, and you'll see why here in just a second. So we're given the graph or the function f of x equals x squared, and we want to use that graph to obtain the graph of x squared plus 3. So when we go over to Desmos, we're going to first look at the graph of x squared, and you can see it's the parabola with the vertex centered at the origin, and that's our parent function. But now when we graph the second function, which was x squared plus 3, if I can get the, you can see it takes the graph of x squared and it shifts it up 3 units. With example 2, we'll see the exact same thing, except this time we're shifting it down. And in example 2, we're comparing x squared, which is our parent function, to x squared minus 4. So I'm going to delete the x squared plus 3 and leave x squared on there. But now let's do x squared minus 4. And you can see that it takes the red graph, which is our parent function x squared, and it shifts the entire graph down 4 units. So what we're looking at there as far as a summary goes is on vertical transformations. Anytime you take a parent function and you add some positive value k to that function, you're going to shift that graph up that many units. And then similarly, if you take the parent function and you subtract some value k from that function, you're going to shift it down that many units. What we're going to look at in examples 3 and 4 are examples of horizontal shifts. So that's where we shift them left or right. And with our first example there, number 3, we're comparing the graph of the square root of x to the graph of the square root of the quantity x minus 2. Notice that the minus 2 is underneath the radical, so it is inside that function that we began with, as opposed to having the square root of x minus 2, which we know already now would be a downward shift of 2 units. We see that this is going to generate a different kind of transformation. And what we notice when we add or subtract inside the function itself is that we get a horizontal shift to the left or the right. What's confusing about these horizontal shifts is that they are counterintuitive to what you would imagine. You can see right here we have x minus 2 underneath the radical. So your first instinct would probably be to say, oh, well, that's going to shift it left 2 units. That's where the counter intuition comes into play. This actually shifts it to the right 2 units. And we're going to look at that graph right now. So let's just first graph the square root of x. There is our parent function, the square root of x. What we want to do is graph the square root of x minus 2 all underneath the radical together. And you can see that it does indeed shift that graph 2 units to the right. And what we would want to consider now is a horizontal shift to the left, and we could see that here in example 4. Example 4, we're doing a plus 4 underneath the radical. So we go back to our example here. Let's take out the minus 2 and let's add 4. And you can see that that shifts it from this red graph to the left 4 units, and it generates our new graph. Now each one of these graphs maintains their original shape. We're only doing vertical and horizontal transformations right now. We're not compressing or stretching these graphs and changing that overall shape in any way at all. So horizontal transformations, when we subtract a value within the confines of that parent function, we're going to get a horizontal shift to the right. Whenever we add a value within the confines of that parent function, we are going to get a horizontal shift to the left, that same number of units. So example 5 would be an example of a combination of these transformations. I want to first point out that we have this plus 3 that's inside the absolute value. The second thing that I'd like to point out is that we have this minus 5, which is outside the absolute value. So let's put everything together, and we're just going to write things out a little bit, and then we'll go over to the graph and see how this all works out. Our parent function, in this case, is the absolute value of x. The plus 3, it is inside the absolute value, so that is going to shift it to the left 3 units. And the minus 5 is outside the absolute value, so that's going to shift it down 5 units. So what we should notice is we're going to graph the absolute value of x, and then we're going to graph this given function, absolute value of x plus 3 minus 5. And we expect to see that our vertex goes to the left 3 units and down 5 units, just based off looking at the information given on that function. So let's do the absolute value of x. And then our second, the function that we're actually looking at is x plus 3. So there we see the left shift 3 units minus 5, and that shifts it down 5 units. So our vertex has gone from 0, 0 to negative 3, negative 5. So it's a left shift and a downward shift in this case. Example 6 and 7, we're going to see vertical stretch and a vertical compression. These two graphs are going to be very similar, and I think I used the absolute value in in the second case, and I used the square root in the first case. So let's just stick with the square root. Okay, for example 6 and example 7, we're going to consider our parent function to be the square root of x. For example 6, it's going to be 2 times the square root of x. And in example 7, we're actually going to do 1/2 of the square root of x. So when we go over here to our graph, we have the square root of x as our parent function. And now we want to look at the next one would be 2 times the square root of x. And the third one is 1/2 the square root of x. And what I wish that graph was a different color. Let's change that. Well, I thought I could change there we go. Make it green. Okay. So the red graph is our parent function, the square root of x. The green graph is 2 times the square root of x. So what we have there is a vertical stretch. We've pulled the square root of x. We've pulled that graph up and away from the x-axis. In the case of the blue graph, which is 1/2 the square root of x, we have a vertical compression. We have actually pushed that graph down closer to the x-axis. And there are a couple of there's actually just 2 rules that we want to observe to determine whether or not we have a vertical stretch or a vertical compression. And those are illustrated right here with this note here, the first note here in red. To get a vertical compression, the multiplier, okay, our constant multiple that's in front of the function, is going to be between 0 and 1. So if you look back at the video, or if you just kind of rewind a little bit and look at the graph of 1/2 the square root of x, 1/2 is definitely between 0 and 1, so that compresses our graph. Anytime our value is greater than 1, we're going to have a vertical stretch by that same factor. So in the the case of 2 times the square root of x. 2 is greater than 1, so we have a vertical stretch by a factor of 2. That graph is pulled up and away from the x-axis, giving us that vertical stretch. Example 8, we're going to see, would be an example of a reflection over the x-axis, and that's simply done by taking the opposite of the given function, of the parent function rather. Go back to our notes here, or our graph, and we are looking at x squared. That's our parent function. Our given function is negative x squared. So whenever you negate that function, that parent function, you reflect it over the x-axis, and then the same transformations can still apply. Let's also consider maybe x cubed. If we take the graph of x cubed, which is not what I'm doing, there we go, x cubed, and then I take the opposite of x cubed and make it negative x cubed. So the red graph is our parent function. The green graph is the reflection of that graph. It reflects it over the x-axis. It takes everything that's below the x-axis and brings it to the top. And likewise, everything that's above the x-axis gets reflected down to the bottom. For our next one, we are negating the x value itself. Not the function, but just the x value. And you can see that right here where I just crossed it out. There we go. We're taking f of x equals the square root of negative x. And when I graph that, again, let's graph our parent function for comparison purposes. So we have the square root of x. Now let's graph the square root of negative x. And you can see that it reflects it over the y-axis. When you negate that x value, you reflect the graph over the y-axis. Now x squared has y-axis symmetry, so you're not going to notice that reflection. The case of the square root of x, again, it's going to be the same thing. Another example we might look at could be just the simple function x itself. If I take the opposite of that, I get the reflection about the y-axis. Example 10, we're going to take these transformations and generate the function that it's asking us to find. So it says find the function that is finally graphed after the following 3 transformations are applied to the graph of y equals absolute value of x. We have a shift to the left of 2 units, we have a shift up of 3 units, and then we reflect it about the y-axis. So let's take those piece by piece, and then we'll put it all together. So our parent function is y equals absolute value of x. Our first transformation is shifting it left 2 units. So remember, a left or right transformation deals with making that transformation inside the parent function. So shifting it to the left is going to be adding, so it's absolute value of x plus 2. Then we want to shift it up 3 units, so that's going to be outside the absolute value. And then we want to reflect it about the y-axis. So reflection about the y-axis is we just negate our x value. And there is our transformed function. So again, we can compare the graphs. We're going to look at absolute value of x. And let's see if all the transformations that we included ended up working out correctly. So we reflect it, so that was the negative x. That's a reflection over the y-axis. We're moving it left 2 units, so we're going to do plus 2. And if I recall, I think it was down 3 units, so minus 3. So we've reflected it, and we've shifted it down and to the left, or to the right rather. And our given function, let's see, I did minus 3, it should have been plus 3, sorry. Okay, so it's up and to the right is our transformation. And if we take that negative off of the x, you'll see this this function right now is shifted left 2 units and up 3. That minus in front of the x is what reflects it over the y-axis, and so that's why we have that shift to the right and then up 3 units. So be cautious, don't get confused and think that the only transformation that occurred here was right 2 units and up 3. We have that reflection over the y-axis, which is critical to the final version of this graph. Example 11, graph the function f of x equals 3 over x minus 2 plus 1. Our parent function in this case is f of x equals 1 over x. And that graph looks like this. Whoa, I crossed the axis. Okay, here's our parent function, 1 over x. This 3 is the same as saying f of x equals 3 times 1 over x. So we're multiplying it by a factor of 3, which means we get a vertical stretch. This minus 2 is in the denominator. That's part of our function itself. So that means we're shifting it to the right 2 units. So we're going to have something like this. And then the plus 1 shifts everything up 1 unit. And our final graph should look like what we have in black here. And I know I've got a lot going on the screen there, but we've just based everything off the parent function. Now let's go back to our calculator and see it a little bit more clearly. So our parent function is 1 over x. Our transformed function is 3 over x minus 2 plus 1. And so that's kind of what we had before. We've taken that red graph, we've shifted it to the right 1 unit. The minus 2, we've shifted it up 1 unit. The minus 2 shifts it to the right 2 units. And then we've also vertically stretched it by a factor of 3, as indicated by the 3 in the numerator. Example 12, going to be kind of the same scenario. We'll just go ahead and graph this on the calculator. We have the square root of 1 minus x and then plus 2. So the minus in front of that x reflects it over the y-axis. This is the same as saying minus, this right here is the same as minus x plus 1. Because the commutative property of addition, we can write it that way. So there's our reflection about the y-axis. This plus 1 is going to shift it to the left 1 unit. The plus 2 should shift it up 2 units. So we'll graph these. Again, let's start off with the parent function to make sure we understand what it visually looks like. And then we're going to graph the transformed function. It was given as 1 minus x. And then I think it was plus 2. So it reflects it about the y-axis. It's shifted to the left 1 unit and then up 2 units. But given our visual right here, if we change this to a plus x, you can see there's the left transformation, and it's up 2 units. But when we negate that x, the whole graph gets flipped around the y-axis. And that was it. So there are our suggested problems. You want to identify the parent function, list the transformations, and then it says draw the graph, but you can graph that on your calculator. So just practice these. Remember, you will have a quiz on Thursday. If you all have questions, just let me know, and I'll be happy to help you out. I hope you all have a great day.